Welcome to this lecture series in number theory. Last time we learned the formal definition of division and some basic properties, along with the definition of prime numbers. Everything was very elementary, and even in this lecture we'll have only a very elementary discussion, but some of the things we will discuss which will not be so basic. Even though the tools will be completely basic, slowly we will be building more and more powerful tools. But for now, what we have is very simple. So let's proceed. Here are some problems for practice. And now let us get started. So what we want to discuss is division with remainder theorem. It's a basic theorem, and let me motivate it. Maybe I'm spending too much time on something too simple, but there is no harm in spending time on such things. So what we have is, suppose we have 17 candies and we want to partition them into 3 bags in such a way that every bag gets an equal amount of candies. What is the best that we can do? Well, the simplest way to do this would be to take a candy, put it in the first bag, then take another candy, put it in the second bag, third candy, put it in the third bag, right? So we have taken care of 3 candies, and then the next 3, and then the next 3, and so on. But now what do we see? We see that we are no longer left with 3 candies. We have less than 3 candies. So as long as we want to equally partition them, either we resort to mutilating at an individual candy, which is not good because you will lose the wrapper and all, so that you can't do. So basically this is the best you can do. You are left with a remainder of candies, and in each bag you have 5 candies. A remainder of 2 candies which you can keep in your pocket and send these bags to the post office. And this is what division with remainder is all about. What you have is, suppose you want to divide a number, call it n, by some divisor d. In our case n is 17 and d is 3. So what you do is you take out as much as you can from n up until the point that you cannot take anything any longer. That's what we did here. So now let me state the general mathematical statement. Yeah, before that I need to talk about the well-ordering principle. Fix any non-empty subset of the natural numbers. The well-ordering principle says that S has a smallest element. What does that mean? It means that is, there is an element S in the set capital S such that S is at most any other element in the set S. So amongst all the elements of the set S, there is one which is smallest. It is a surprisingly or deceptively simple statement, but it is at the backbone of discrete mathematics. If you are feeling that this is, of course, an obvious statement or something, yes, I agree with you, this is an obvious statement, but let me still point out a pitfall. Consider the set of all positive real numbers. If, suppose T is used to denote all positive real numbers, and 0 is not positive, all positive real numbers, this set does not have a smallest element. Any element you pick here, you can halve it. Suppose somebody says that suppose somebody produces an element in capital T and claims that it is the smallest element of T. Well, what you can do is you can divide that by 2, and still that thing is in capital T, and of course it is smaller than little t. Any element of capital T can be divided by 2 to obtain a yet smaller element. So there is no smallest element in capital T. And you may have studied physics in high school, in which you may have encountered infinitesimals, something like delta T, where most likely the instructor mentioned that this is an element so small that you cannot get anything smaller than it or something like that. That is all lies. Anyway, so natural numbers have this property that you pick any non-empty subset, it will possess a smallest element in it. All right. And well ordering principle is something that I would like you to learn very well. In this course, we will use it, and to get to get up to speed on that, you can watch the corresponding videos in my Kickstart playlist. So there are some 4 or 5 videos dedicated to the well ordering principle in that playlist, and I encourage you to watch them. All right. So what is the division with remainder theorem? What we have, we start with a natural number d. Then for any integer a, there exist unique integers q and r with the following properties, that a is dq plus r and r is in this range. Now in our candy example, a was 17, d was 3, q was 5 and r was 2. Right? So what are you having? You have some a candies. You want to divide it into d bags. A candies are to be divided equally in d bags, and there will be some remainder left with you, but that remainder that will be left can be 0, but cannot be more than d. I mean, you can... Yeah, so let me not say too much about it. Just think about the statement with reference to the concrete example that we saw, if this is throwing you off. All right, and now we want to prove it formally. This is not an intuitive challenge. This statement is so trivial, so intuitively simple, that one may not even feel the need to prove it. But still, it requires a proof. This is not some independent, or this is not an axiom in mathematics. This is something that we can prove. Okay, so let's get down to proving it. And the proof follows the idea that we saw in the concrete example. You extract from a as much as you can before you can't any longer. So define this set. Define this set, but we do not want to consider negative numbers in this set. We just want to so maybe I will modify this a little bit, because a could be negative. I mean, here a could very well be negative. So okay, so to make my life simpler, I will prove it only in the case when a is positive and leave to you the general case. So proof for a positive. This will help me explain the proof a little better. Proof for a positive. So define this set S as a minus dn, where n starts from 0 and goes up to whatever, as large as it needs to be. But we do not want to collect negative numbers or the number 0 in we are fine with collecting the number 0. That's fine. So this is our set. What are we doing? We are collecting all such numbers which are non-negative. If you take n too big, then ultimately this will become negative. So beyond that n, we will just not consider those n, basically. All right, so I hope this set is clear. And since this is a non-empty subset of this guy, so thus S is a non-empty subset of this guy. What is this guy? This is the set of all the whole numbers. So recall, this is the set of all the whole numbers. I stated the well ordering principle for natural numbers, but the exact same statement holds for whole numbers, of course. You pick any non-empty subset of the whole numbers, it will have a smallest element. Okay, so S is a non-empty subset of the whole numbers. Why is it non-empty? Well, if you take n is equal to 0, you get A. A is certainly here. A is here because you take n is equal to 0. You get A in this part. And A is clearly here because A is positive. So it is in both and hence it is in S. So therefore S is non-empty. And thus, by the well-ordering principle, S has a smallest element or the smallest element because there is only one smallest element. And we will call this element R. Okay. So it is clear, note that A is equal to dq plus R, or maybe I'll write it this way. So R is equal to A minus dq for some q. Why? Because R, after all, is an element here, and hence in particular R is an element of this set, and any element of this set can be written in this fashion for some non-negative integer q. That's how this set is defined. So R is equal to this for some q non-negative, but we claim that R is in this range. Okay, so why is that? Suppose not. Then what is R minus D? R minus D is A minus dq minus D, which is A minus D times q plus 1. So R minus D is equal to that, and hence is an element here. But by assumption that R is not in the range written, means that R is at least D, and hence R minus D is at least 0. Since R minus D is at least 0, R minus D is also here. So what we see is that R minus D is both here and there, and hence in the intersection. Therefore, R minus D is an element of S. But R minus D is strictly smaller than R. But what was R? R was the smallest element of S. And here we have produced a yet smaller element in S, which is a contradiction. The choice of R was that it was the smallest element of the set S. But this reasoning has produced a yet smaller element in S under the assumption that the claim is false. Hence the claim must be true. So we have proven this claim. Having said all this, let me give you a high-level picture of the proof. What was the choice of R trying to do? What we are achieving here is we are taking out as much from A as we can. That's why we chose the smallest element in S. We are extracting multiples of D from A, and we will leave at the point where we cannot extract any more, lest we take away so much that we are left with something negative. So that's the philosophy behind this step, and then all of the rest of the reasoning just follows itself. So we have proven the existence of Q and R. This proves existence of this claim along with this statement shows that there do exist Q and R with this property. Existence is settled. What about uniqueness? So for uniqueness, suppose we have Q1 and R1 in integers such that, maybe I'll need an extra page. So suppose we have Q1 and R1 in Z such that A is equal to dQ1 plus R1 and R1 is in this range. And we also have another pair. And we have Q2 and R2 integers such that A is dQ2 plus R2 and R2 is in this range. What uniqueness means is that want to show that. So this notation means want to show that Q1 is equal to Q2 and R1 is equal to R2. Okay. So by these two equations, we have these two equations. If we subtract them, what do we get? We get 0 is equal to d times Q1 minus Q2 plus R1 minus R2, which implies R2 minus R1 is equal to d times Q1 minus Q2, which implies d divides R1 minus R2, right? But R1 and R2 are both in this range 0 to d. D excluded, 0 included. So R1 minus R2 is something which is in magnitude strictly smaller than D. So here is the important point to note. Note that the magnitude of this is strictly smaller than D. That's because both of them are in this range. So convince yourself of the truth of this. So if you have some positive integer which divides something non-zero, if R1 and R2 were different, then what we would have is D is dividing something non-zero, but that something has magnitude smaller than D, which is not possible, right? If D divides something, if D divides some integer capital N, and N is non-zero, then this is necessary. Therefore, since we have the magnitude of this difference is smaller than D, it follows that R1 minus R2 must be 0. So this implies that R1 minus R2 is 0. That's the only possibility, which implies R1 is equal to R2, which also implies that Q1 is equal to Q2. Why is that? Because if R1 and R2 are the same, Q1 and Q2 are both solutions of this linear equation, and therefore they are the same. In fact, each of them is equal to A minus R upon D, where R is the common value which R1 and R2 are. Right. So that shows uniqueness. So nothing very complicated is going on. We are just executing the simple observation that we saw when we were discussing the candy example. We are just doing the formal mathematics of it. And the linchpin of this argument is the well-ordering principle, the fact that this S has a smallest element. I understand that if this is the first time you're looking at such an argument, it may seem a little foreign, but stay on it. This reasoning may just obscure the simplicity of this statement, but you have to overcome that obscurity. Anyway, so now let us see some examples. So let's appreciate the power of this very, very simple statement. So first we want to prove that this expression is always an integer, no matter what integer n you pick. Now you may say that, well, this is equal to what? This is equal to 1 square plus 2 square plus ... n squared. Perhaps you know this formula. And then since this is clearly an integer, we are done. But suppose you didn't know this formula, right? Here we got lucky. This thing has a nice formula, but I mean, this is a result of a nice sum, but not all the time we may be able to come up with such a simple interpretation of such things. So let's see a very fundamental, more basic approach. And given the tools we have, the solution will be a little bit lengthy. As we develop more tools, this is something that, again, you can do mentally. But for now, what are we interested in? we are just trying to prove that this number is divisible by 6. That's exactly what it means to say that this is an integer. We want to prove that this is divisible by 6. And the division with remainder theorem says that something is divisible by 6. So let's say capital N. Capital N is divisible by 6 if and only if the remainder, let me write a q here, 6q plus r. What does the division with remainder theorem say? That any integer capital N can be written as 6q plus r, where r is in this range. And n is divisible by 6 precisely when the remainder is 0. So I didn't say that in the previous slide, but if d is some positive integer and a is some other integer, then a is divisible by d if and only if, when you apply the division with remainder theorem and obtain r in this range, then r is 0. So divisibility can be equivalently stated by saying that the remainder that you obtain is 0. So I hope that point is clear. So we are trying to show that the remainder of this when divided by 6 is 0. And now there is a natural approach. So say n is of this form, 6k plus r, where k is an integer and r is in this range. Right? That's immediately by applying the division with remainder theorem. We are not trying to show that r is 0. We are not trying to show that n is divisible by 6. We are trying to show that this horrible thing is divisible by 6. But anyway, so let me proceed and you will see the point of doing this. Okay, so what is this expression? This expression is 6k plus r, 6k plus r plus 1, and here we'll see 12k plus 2r plus 1. All I did was substitute in place of n this expression. And now if you do the algebra, you will see that this is equal to 6 times some integer, some horrible integer that we do not want to compute, plus r into r plus 1 into 2r plus 1. So it's important that you agree with this step, right? I'm just doing the basic algebra. The first term you take out, you will see certainly something that is divisible by 6. Then you may take out this term that is also divisible by 6. It is already featuring 2 6s. And so on and so on. The only term that will not feature a 6 is this, which I have written out separately. So this is of the form 6 times some integer plus that. So to check if this is divisible by 6, we just need to check for 6 different values of r. When r is 0, when r is 1, and so on up until r is 5, because r is in this range. So when r is 0, is this divisible by 6? Yes, it is, because when r is 0, this is 0. When r is 1, then what happens? So when r is 1, when r is 0, then this is 0. When r is 1, then what is this? Then this is 1 times 2 times 3, which is 6, certainly divisible by 6. When r is 2, this thing is what? This is 2 times 3 times 5, which is divisible by 6, because that is equal to 6 times 5, 30. And so on. You can compute for other values, 3 and 4 and 5, up until r is equal to 5. So you'll see every time this term is divisible by 6, and that's it. So that shows that no matter what n you pick, this will be divisible by 6. So the division with remainder theorem reduces this problem, which was an infinite problem. You would have to prove it for infinitely many n's, to checking it only for 6 values of n, namely 0 up to 5, where you can just do a computation and verify. So we have proven the first one. Now let's see some other example. So we want to show that the square of any integer is either divisible by 3 or is of this form, 3k plus 1. So whenever you square an integer, you will never obtain an integer which can be written as 3k plus 2. Very interesting. You can experiment if you don't believe this. So let's prove why is this true. So let n be some arbitrary integer. And since we are trying to, we want to study n squared in relation to how it behaves when it is divided by 3. Again, it is meaningful to express n as 3k plus r, where r is in this range. Right? So thus, n squared is basic algebra 9k squared plus 6kr plus r square, which is 3 times some garbage plus r square. What is the garbage? Let me write down. We don't care, but still. 2kr. Yeah. Now, r square can take how many different values? If r is 0, this is equal to 0. If r is 1, this is equal to 1. If r is 2, this is equal to 4, but I will write that as 3 plus 1. And in case r is 0 or 1, clearly n square is of the form 3 times some garbage, which I'm writing as capital K, plus either 0 or 1. But in this last case, this 3 I will absorb here. In the last case, it would be 3 times garbage plus 1 plus 1. So you can always express the square of any integer as either that or that, depending on whether r was 0 or not. If r is 0, n square is of this form. If r is non-zero, then it is of this form. Great. 2 more examples and then we'll finish. So we want to show that whenever x and y are 2 integers such that the sum of their squares is divisible by 3, then 3 divides both of them. Not obvious, right? But we know, so since we know that by the previous example, we know x square is of the form 3k plus r, where r is either 0 or 1. That's what we saw in the previous page. And y square is similarly 3l plus s, where s is either 0 or 1. Right? So therefore, x square plus y square is 3k plus l plus r plus s. And what do we know? We are given, and suppose this happens, this is given to us. So 3 divides this guy. 3 already divides that guy. So 3 must also divide the remaining guy. 3 divides r plus s. Hope this is clear. 3 divides this as given. 3 of course divides that. So 3 must divide what is left. And r and s are in this region 0, 1. R can take 2 different values, and same for s. When can this happen? For what values of r and s in this region can this happen? Just think about it. This can happen only when r and s are both 0. This implies r and s are both 0. And therefore, x square is 3k and y square is 3l, and hence both. Yeah, so what does this show? So this shows that x square, 3 divides x square, and 3 divides y square. But what did we want to show? We wanted to show that 3 divides x and 3 divides y. So to finish, we will use this statement. If for an integer 3 divides z square, then 3 divides z. Once we do this, we will be finished. So again, why is that? Say z is 3k plus r, with r in this region. Z square is, we want to show that r is 0. right? We want to show 3 divides z, so we want to show that r is 0. That's what we want to show. But we are given that z square is divisible by 3. So what is z square? Z square is 9k square plus 6kr plus r squared, which is 3 times some garbage plus r squared. Again, z square is divisible by 3. Z square is divisible by 3. This is of course divisible by 3. So therefore r square is divisible by 3. But r can take values in this region. So r is either 0 or 1 or 2. If r is 0, then we are done. If r is 1, then this cannot be true because 1 square is 1 and 3 doesn't divide 1. If r is 2, then again this cannot be true because 3 doesn't divide 4. So r must be 0. So r must be 0, and that's it. We wanted to show r is 0 because we wanted to show 3 divides z, and we have shown r is 0, and that finishes this statement, and that we apply here to deduce that 3 divides x and 3 divides y. So that's it. This is where I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.